Good morning, everybody. Myself, I'm Ahmed Osman. I'm presenting Nokia. I lead the network optimization business for Nokia. And today, we're going to talk about artificial intelligence and machine learning. How can we bring this capability to the private LTE and the 5G utility space? We're going to discuss exciting use cases today about how AI ML can help in areas like network deployment and network operations. Today's agenda, we're going to talk a little bit, light talk about machine learning in general, the technology, the enabler. Then we're going to talk about some considerations, how we can bring this technology and how to kind of deploy it in the most efficient way. I'm also going to be talking a little bit about use cases in the space of network operations and management. And I'm going to hand over to Klaus, my colleague. He will talk a little bit about his part in today's presentation. Klaus.
Good morning, everyone. My name is Klaus Metnitzer. I am part of the Services Execution Excellence team in Nokia. It's a fancy title, but the fun part of my job is really try to find enhancements to make things better, cheaper, easier for our customers. And one thing that I'm going to talk about today is how we integrated AI in our deployment process when we deploy cell sites, and how it improves the quality for our customer, and how also it improved efficiency for us and for our customers.
Thanks, Klaus. Let's get started. So machine learning. We have been hearing a lot about artificial intelligence and machine learning over the last few days, so we're going to crack it a little bit here. So I'm going to start by kind of talking a little bit about what does it take to introduce AI ML in the utility space, but in general in any industry. Because of it's a new technology, there are certain considerations. So the way you need to build machine learning capabilities is really starting with the people. Artificial intelligence is all about automation, but guess what? It needs really good people to build it. So in terms of team capabilities that you need to have in your organization, you need to have people who knows data. Those are very important folks. Those know exactly what types of data are existing in your network. And data comes in so many different shapes and forms. Structured data, unstructured data, textual data, images, so on and so forth, so many of them. And this is what AI and ML needs, data and lots of data. So data engineering is a very critical skill set to build machine learning models. And with that, also come after that, the ability to actually have the skill set about modeling. There are so many models out there doing and solving so many problem statements. What's the right one for you? Those are the kind of questions people with the right skill set in the AI, ML modeling space will help you to answer. And then we sometimes do not really focus on this. This is really key, really important. Your domain experts. Eventually, AI, ML models will help you to automate, but we need to make sure that they are guided, that they're providing the right insights. We hear about hallucinations in AI and those kind of things. We need people who knows those kind of systems. Those can help us. We can actually apply a certain reward penalty schemes with the feedback of users so we can able to kind of build better models, right? Now, after you have the right people, you need to engineer your data. So you will be collecting a lot of data. And sometimes the data is not good, it's corrupted. How we would know that, how we can signal that. Then you need to process all sorts of data, right? So you need to have the right infrastructure, compute, to be able to do that. And then you have missing data all over the place. What can you do with that? Do you need to impute missing data? Do you need to discard some of the data? Those are tough decisions to make. And then comes the modeling, right? Again, it's all about the business problem you're trying to solve, right? There's so many business problems out there, so many use cases. And once you know your exact business problem, it becomes easier to choose the right models and be able to train and validate, an array of models to select the best ones. I just here wanted to kind of have a very nice summary of what kind of machine learning capabilities or models are out there. So, and some of them are really non-formal, outside the telco space even, but just give you an idea about some of those types of machine learning capabilities. So, supervised learning is really where you're learning from data that has labels. Things like you have a fault in your network. It did happen. It's a label. Or you didn't have a fault. And what kind of factors that cause that, right? Unsupervised is mostly you don't have labels. So it's more about exploring the data as is, finding structures, patterns. We hear about clustering. A lot of exciting use cases in that space. And then finally, reinforced learning. This is about how, for example, autonomous vehicles work. They make decisions, and then they kind of calibrate their systems based on, again, reward and penalties. How good are they doing? Those kind of models fall under reinforced learning. Now, I'm going to talk a little bit about some of the considerations of introducing machine learning models into the network. So, again, I keep on mentioning my theme is data, it's so many data, but here you're dealing with so many network elements in your fan. Not just your radio access network, but so many devices, connected devices, right? Different manufacturers. So how can you collect this data again? How you process it, store it, right? This is an important part of building machine learning models, really to have the right data to do so. And then, do you have the right infrastructure to process and store the data? Do you have the right compute? Where your models sit, where your infrastructure of automation sits. Is it in a centralized data center, or is it closer to your edge, right? Those are some considerations in introducing automation and machine learning in general for utilities fan. And then you're just not building one model or two. You're building so many use cases, a lot of automation. So you need workflow. You need digital platforms that are secure. Things like Kubernetes architecture that allow you to scale the resources you need to build those use cases and get the right amount of resources. So this is all important considerations when we start talking about machine learning and automation. And again, the infrastructure choice. Are you doing bare metal? Are you doing cloud? Again, those are important discussions in that space. Today, we're going to discuss a little bit of selective use cases in particularly network operations management, and Klaus is going to talk a little bit about network deployment. This is just a snapshot of some of the use cases we in Nokia have been working with over the last few years. There are so many use cases out there. This is just a snapshot of what we are doing today. So we're going to talk a little bit today about anomalies detection. It's an important aspect of, and good example of machine learning capabilities is it's really when you look at your systems, you know how systems operate. You understand the normal underlying conditions of your system. But then sometimes there are anomalies. Things like sudden increase in traffic or sudden change in the pattern of usage of your devices. How can you spot those? Those sometimes mean something is going wrong. And it could be internal or external. External could be environmental factors, right? But sometimes those anomalies are caused by internal reasons. You need to find out that. You need to do proper root cause analysis, correlating so much data to be able to find those insights. And then fault prediction. The utilities, the networks, they're very critical to ensure network reliability and availability. So if you are able 1, 2, 3 days in advance to predict a failure, that's a great capability. And that's one of the things, in one of the use cases we're going to discuss. And as well, when it comes to capacity, maybe not today, but the network is growing. The amount of connected devices increase. We have been all hearing about AMI 2.0. Very exciting use cases. A lot of increased device penetration, smart metering, increased data requirements. Do you have the right capacity today? Do you have the right capacity a few years down the road? This is a topic of machine learning as well, about traffic forecasting. Is your network today able to meet the demand a few years down the road? Those are the kind of questions we can answer with those models. But also, today, if you have a capacity bottleneck, and some utilities, they do have multiple bands, right? Are you balancing the traffic the right way between those different bands? Machine learning also can help here, can help you to automatically balance your devices between the bands you have. So you can get the right service levels in all those devices. So this is, again, another set of examples we're going to be talking about today. I'm going to go a little bit in details in the next few slides. So, sorry. So here we're going to start with anomaly detection. And if you look at the graphs, it's so clear. All of a sudden, something happened. This is how anomaly works. The way it works is you understand what the normal range of your data is. And all of a sudden, something happens. Your KPIs, your metrics just shoot to the roof. Some of those anomalies are short-lived. They come and go. A lot of that might be attributed to environmental factors. Hurricanes, heavy rain, winds, so on and so forth. Those are the things maybe you don't have to worry so much about. But sometimes anomalies come and they stay. This is where you have a problem. And you need to do very good root cause analysis. And you see in one of the charts, this is the second one up there, an anomaly came and it stayed. So what's going on there? This is where you apply RCA, root cause analysis. So much data out there, you need to correlate data coming from your fault management, configuration management, performance management, logs of your elements. And that's how you can reach to a very good insight into what's the root cause of this problem. And that helps you to automate the corrections, right? So for that particular case, there has been a change in the configuration in one of the sites in your network, right? And that change just caused that kind of anomaly. So a very normal course of action that would you revert the change, kind of understand better why it caused that kind of change. Sometimes the anomaly is because you have a fault in your network. There's an active alarm, and somebody has to go and check the site or remotely do some sort of troubleshooting. That's the kind of visibility you need. You need to understand why your system is going through this kind of anomaly. If I talk a little bit more and expand on that, in the area of anomaly detection, there is a lot of exciting research and models out there. And it really depends on the type of anomaly we're dealing with. Some of the anomalies are related to data that are time series based. So this is data that varies time. In that space, there are very good models out there. Meta, quite interesting. They have a model called Profit that helps us to model the time dependency of data and help us to spot and find those anomalies. If your data is not exactly time series based, you start looking more into clustering, regression. Bottom line is, you have a lot of models out there. Once you understand your problem specifics, it's very easy for you to find the right match. And all those models are open source. You can get them so easily, train them. So no issues at all there. Then you have problem, or maybe a lot of problems. You need to kind of rank your problems. So automatically kind of find your top offenders. Where I should focus my energy, right? And then with that, you need to do the root cause analysis we have been discussing. Bringing all this data, correlating a lot of data together, even sometimes building more sophisticated classification models that can tell you, oh, this anomaly because you did this or you did that. And that is what's going to help you to actually craft the right changes, the right recommendations and corrective actions. So it's all a connected workflow. It starts by spotting an anomaly and then going through that flow to be able to get to a point where you actually rectify the anomaly in the system. Here we start talking a little bit about capacity. Very interesting because in the CSP world, this is a very regular topic. Every day we talk about the current capacity, the needed capacity, what I'm going to need 1 year, 2 years down the road, what kind of bands I need to add to my network. A lot of people talk about the layered approach of networks where you have multiple bands. Do you need to upgrade your equipment? So many business decisions that impact your spending, right? So machine learning and AI can help a lot in that space. So again, with the idea of time-based forecasting with the models like Profit and so on and so forth, you can, and you see this second chart, you can see your traffic growth. You can model that. You can see where, at what time in time, you're going to start having problems in your network. And it's not about just congestion in the matter of I cannot allow more users to access. It's even sometimes to the point of I have all my users, but they're not getting the right service levels in terms of speed, latency, packet loss. That happens when you have a lot of users. So you want to be able to forecast that. And machine learning can help a lot in that space. And then to kind of expand a little bit on the capacity topic today, right? The beauty of LTE and 5G networks is really the optimization angle to it. You can easily optimize so many aspects of your network. Your existing capacity is not set in stone. You can extract more with optimization. And this use case is all about managing and optimizing the network to even have more capacity than what the existing resources have, extracting more out of it. So here this use case is about if you have multiple bands in your network, do you have the right distribution of users or devices between those bands? In this specific use case, we have been trying to look into user throughput, which is a very important metric in the CSP space. Are we getting the best user experience in terms of user throughput? And the answer is no. You do not have, by design, the right distribution of users because cellular networks are not very simple. It's not about the number of users you have, it's about the radio conditions they have. That kind of dictate how they see the network and how they kind of get the quality of the network, right? So with that kind of complexity, machine learning is very important. This use case is trying to automatically reshuffle, rebalance the traffic between the different bands that does exist in the network. Then the objective here is to maximize what a user throughput a user can get. Now, you can easily replace user throughput here with latency, which is more relatable to the utility space. You have a lot of applications that require low latency of your end devices. You can even replace that with reliability, packet loss, right? The concept is still the same. How we do it? It's a simple approach. You can, through machine learning, through models like regression, and there's so many variants of it, exponential, nth order, you can kind of map the relation between your number of users and the experience they get in terms of throughput, latency, packet loss, and so on and so forth. Once you have that understanding, there is another exciting part of machine learning, sometimes overlooked, but it's really important. It's optimization. It's actually an older, even generation behind the mainstream machine learning. Optimization is all about the best, most efficient use of your existing resources. That's the idea. Once we establish the relation between the number of users and the corresponding service levels, we can build those optimization algorithms. They're sitting there, they have all the right inputs, and they can automatically decide how we can distribute the users between the bands we have, the devices between the bands we have. And their sole objective is to either maximize or minimize a certain performance metric. So in terms of throughput, that would be a maximization problem. In terms of latency, packet loss, that would be a minimization problem. So that kind of use cases are very important. We have been working with them for a lot of years now, and they're very, very efficient to kind of extract more gain from your existing resources. You don't need to upgrade at this point in time. That doesn't conflict with the fact that you still need to forecast, because 1 year, 2 years down the road, you might need that kind of expansion. You might need additional band. You might even try to get more bandwidth in your existing band. Those are the kind of questions those traffic forecasts and optimization use cases can answer. I'm going to end with this use case, at least my part, and I think it's the most important in the utility space. Your radio access network should be very reliable. There is no room here for service interruption, downtime, outages. So the problem with those kind of scenarios is if they happen, it's emergency mode. Everybody is running, we need to fix it. What if we can predict those events days in advance, and we can take proactive actions? That's the value. We can reduce or even eliminate that downtime. And it's a very exciting use case that we built for one of our CSPs. And the kind of those use cases, and this is the main theme in machine learning: data, lots of data, and so many data sources. And you need to figure out what's really needed. But for this specific use case, from a radio access network perspective, you need to get historical records of your fault management, cases where those critical faults already happened. You need to get a lot of data around the performance of your access network, the configuration, even getting, which is very exciting, logs from the different network elements, textual data. You can use textual data to augment those models and make them more robust and provide better accuracy. And this is an exciting space because today, when people talk about AI, OpenAI, ChatGPT, it's all about text, right? And in machine learning as well, text is a very essential part of what models we can build. So once you have this data, right, you start to think, how can I solve this problem? What kind of models I have out there? And for those who are kind of familiar with the machine learning AI space, the state-of-the-art models today are neural networks, right? And there are different variants of those models. When we initially approached this problem, we were thinking that it's a sequential problem. Think of certain events happened, and then there was a critical fault detected. Think of A, B, C, D happened, and then a critical fault happened. Well, we tried that. We tried neural networks that are designed to solve those problems. LSTM, state of the art. It's part of the recurrent neural networks family. We were expecting good results. We didn't get good results, really bad results. And then we went back and started thinking, well, maybe the problem is not sequential. Maybe it's not A, B, C, D causing a fault. Maybe it's a B, A, C, D or a D, C, A, B. And we were right. Then the radio access network doesn't work like that. It's not about the sequence of events. Sometimes the events are random, but they do mean something. And with that kind of different problem statement, there are other family of machine learning models that can help. And here we start talking more about the likes of XGBoost, Random Forest, which are more designed to solve those kind of problems where there is no sequential dependency. And we were right. The results achieved from those models, and you can see some of that on the right here, are pretty impressive. We're talking about forecasting critical faults in the access network up to 4 days in advance. Imagine what we can do in 4 days. We can prevent a lot of problems. And I have some matrix here that kind of explain how good the model was, precision recall, some technical terms. To simplify things, what is precision? It's really if you make 10 predictions, how many times you're correct. So it measures how good your accuracy of prediction is. Recall is like you have 20 faults. How many you were able to predict correctly? So both together are very important metrics of those kind of models. And if you see the results, pretty impressive. 80% precision, how good we are predicting. 70% recall of all critical faults. This kind of capability is key if we want reliable networks that are always available. So we can take proactive actions like this one. And with that, I'm going to hand over to my colleague Klaus. He'll talk more about network deployment and how AI ML can help in that space. Klaus, to you.
Yeah, hello everybody. So if you think about it, Ahmed is able to predict the future at 80% accuracy. I think that's a pretty cool feature, and that's really where AI is a fantastic tool to use. So I'm going to show you a few use cases where we use AI in the deployment world. And one might think, deployment, this is really where we go out, right? We install antennas on towers, and we run cables. Why would you use AI for that? And I was there about 18 months ago, and was thinking the same thing. How could we use AI? And then my world changed, and it truly changed in the last couple of months. And I'm going to go over a few use cases in the top row. This is all deploy related. And then I also wanted to show you some health and safety AI use cases we do to improve safety for our crews on site. And so the first one is a very, is probably one of the most popular one we do. This is automatic asset recognition on towers, where you identify the equipment that's on a tower and basically catalog it and provide databases. The next one is the automated quality audit that we do, and I will go over showing you how AI is now better than humans in doing that. The third one is a brand new thing that we started very recently, and this is called automatic pole assessment. This is where we take pictures of drones and actually identify all the equipment, measure the height of the pole, measure the cables, identify the insulators, identify all the equipment on the pole with just 30 pictures, and it's all done fully automatically. And then the second row, health and safety, right? Health and safety, everybody cares about that. It's the top priority for everyone, and so it is for Nokia. So site hazard identification, we have a feature called hazard identification lens, and I'll go over that, what that does. And then we identify the personal protective equipment for our crews, make sure that they wear the right gear when they install equipment on site. And the last one is the crew check-in, check-out verification. So let me go into the asset recognition with AI. Difficult word. So what we do is we have a drone that flies around the red center. It does a loop on the tower where all the equipment is, and takes about 200 to 300 pictures. Those pictures are then automatically uploaded to the platform, and the platform stitches it together with a technology called photogrammetry. And what that does is it gives us a 3D representation of all of the equipment on that tower. Then we have a database that has the form factor of every piece of equipment that could be on a tower in the United States. It's about 90,000 different pieces of equipment, CommScope antennas, Nokia radios, and everything. And that data is then compared to that database, and AI then selects match and gives us a response back and says, you have 3 CommScope antennas model XYZ on your tower, you have 10 Nokia radios, you have 5 squids or 1 squid on there, whatever it is. And that data is then, we use that and provide that back to our customers. And what we've learned is a lot of our customers are often shocked of what's on the tower and what they thought they have on the tower. So that helps us, keeping the record straight, making sure that, everything that our customer think is on the tower is actually on the tower as well. And then the next one is a really cool one. We started this in January. This is how we identify quality issues on a site. So let's say I'm an installer on a site, right? I'm up on the tower, and so I'm now done with my installation of the cables to the antennas. You can see in the bottom right, the picture. So I'm hanging up there on the tower, right, and I snap that picture and I'm done with my work. The usual way it would work is I snap that picture, I then upload it to the cloud. A day later, one of our quality engineers will review the data and then get back to you and say, this is approved or rejected. So there is about a 24-hour delay, and then once we approve it with our own quality in-house team, then it goes over to the customer. They do the exact same thing again. They have quality engineers looking at hundreds of pictures and then, approve or reject it. We have customers where we have up to 600 pictures per site. We have customers where it takes about 150 pictures per site. So you can imagine there is a lot of overhead that the teams have to actually review all these pictures and the quality audits. So then in January we said, let's do a AI shadow mode. So what we did is, while our quality auditors were approving those pictures, we ran AI in the background and had AI approve or reject those pictures at the same time. And we thought, so it's going to be about a 6-month process where AI will catch up to an acceptable level. But little did we know that 3 months later, AI had surpassed the accuracy of our human auditors and actually had found more issues than the humans did before. Because the beauty of this AI solution is it does not only look for one specific issue. So for instance here, we were identifying the weatherproofing on the bottom of the connector. But AI at the same time also checks for bending radius of the cable It also checks for the color coding, and it does all of that within a 3-second response time. So again, if I'm the guy on the tower, right, I take the picture, and then 3 seconds later, I have the approval back from AI that the quality is acceptable. I know now, well, I don't have to come back up here because I don't have to wait for somebody else to approve it whenever they have time. And then the cherry on top of was one of our customers saw how accurate AI was with doing these quality audits, and they said, why would we have to spend our time again to approve what was already pre-approved? These models were built on our criteria, so we don't need to redo what the AI has done already. So what that really did is, back to the guy on the tower, was when he gets the approval back from AI, he already knew that it was approved by Nokia, but also it had the end approval by the customer. So he literally knows that he does not have to go back to that site. And on some projects, this reduced site revisits by 60%. And we all know these revisits are super expensive, take time, and nobody is happy about those. The one other thing that our model did, which took quite a while to develop that technology, was if it's rejected, it actually tells you why it is rejected. The model is smart enough to actually can tell these are jumper cables that are attached to an antenna, and if it rejects it, it will tell you because there is a gap in the insulation, for instance, or it can even identify torque issues where it, through thousands and thousands of pictures, it can identify if there is a small gap between the nut and the antenna, and it would highlight things we didn't even think of that it could do that. And all of that was because we had hundreds of thousands of pictures from previous installations that identified bad quality and good quality. And as anybody who works with AI can tell, this is really where AI works really great. If you can teach it and you have enough data to teach it, right? So that was a huge success rate. Our custom or our installers are really happy about this. Now the response time is a lot quicker, and I have a little data to prove this. So if you look at the bottom of these two charts, before we started the AI project, it took us on average about 28 days to get a closeout package approved through the Nokia quality auditors and then through our customers. Once we started AI, it got down to 6 days, and then it's actually way much further down right now. 6 days was only because not everything still was approved by AI. There were still some manual approvals done, but it's we're targeting about 1 day right now to get everything done and processed, because there shouldn't be any humans involved in the process anymore. So overall, this gave us a 78% cycle time reduction for the entire closeout process. What that means is, for us and our installation companies, everybody gets their money quicker. The customer is happier because the site gets on air earlier. They start making money. They can use the network earlier. So it's truly a win-win-win situation for everybody. All right. And then this one is a really cool one we started recently, and this is about assessing all those utility poles out in the field. And what we do here is we identify, let's say the South LA area, and let's say we need to identify all the utility poles in that area. So we identify, okay, where do we need to go, and then we send our drone pilots out to those city areas, and then they fly those poles. One pilot can fly about 200 poles a day, and all that data is then uploaded to our platform. And when I say fly a pole, that means it takes them about 2 minutes per pole. They fly one circle, one loop around the pole. Takes about 60 pictures, and those 60 pictures, that data is enough for our AI to extract all of the information for the pole. That means the assets on the pole, the height of the cable, the sagging of the cable in between. And that then gives us a database that we then give to our customers along with all the pictures that are needed. But most of our customers, they don't really need the pictures. They're really interested in, okay, identify all the locations, identify what's on these poles, because I want to identify, maybe I want to add these LTE edge devices on it. I need to identify locations on those poles. What would it take? And we're literally capturing thousands of poles on a daily basis now, because this has been very successful. The cherry on top here is really also, you have all of this on a digital platform. So anytime you want to revisit for another reason, you can go back, pull up the pictures of all of their poles, pull up the inventory, all the measurements, and it'll be there until the next time you have to refresh it. This is also one of the big reasons was Geo 95 in California, where the government mandated to start collecting the asset information on all of these poles. And then let's go a little bit into health and safety as well. So we at Nokia, we always want to find ways of how can we improve our safety, the safety of our crews on site. What can we do without increasing the time or the effort on site for the crews, without making them do something that makes no sense. And one of the things that has a lot of success is our hazard lens. What the hazard lens is our crew arrives on site, they take out their phone out, start the app, and the app starts then this hazard lens. It takes they swivel around 360 degrees, and in real time, the app then identifies, here we have 11 hazards, but it's a lot more than that, any potential hazard on site, and logs it. And the reason is not because we don't trust the crew not to be able to see what a hazard is or not. We're trying to create a database of which sites have what potential hazards, so that we can categorize it the next time we can go to a site. And also, in case we find something that the owner for that site does not know about, and it really needs to be fixed. Let's say we have a lot of rust on a ladder or a broken ladder, stuff that really needs to be fixed. We also want to log that, identify that, report it back to the owner so it can be fixed, so nobody gets hurt when they are on site. So that is the hazard lens. And then the last one is the PPE identification. So this is, again, when our crew starts their day in the morning, they go out to the site, they take out the app, and then they check in. And with the check-in, they take a quick selfie of themselves and the crew itself. And then this is where AI then identifies, are they wearing all the safety gear, the safety harness, the shoes, the protective shoes, the glasses, and of course the helmet. And then it approves it or rejects it. If it's rejected, that does not mean they're not allowed to start work, but it sets a flag for our construction managers, and they will review this later on. And if it's really the crew didn't wear it, or the crew over time, often continues to fail these checks, then we'll have a more serious talk with them. And all we're trying to do here is we're trying to improve the adherence to wearing safety gear while on site. They do that at the end of the day as well. So that we can, there is two reasons for that. One is, okay, we want another picture to make sure, is the entire crew still on site, has somebody left, or has somebody joined them? And then the other one is, we want to know when they stopped work. Because if something happens on site afterwards, we want to be sure is the crew still there or have they left. So with all these records, we have seen a real trend on improving safety. The crews are now truly wearing the gear earlier in the day already, because they know, well, somebody's going to look at that picture, and if I don't wear it, then I'll get in trouble, so I might just wear it anyway, right? And that's kind of what we are trying to do, is, wear your safety gear while you're inside. It's a dangerous area, and it's totally worth it to do it. So that's how we improved safety out there. This is mandated for our crews now. Since a couple of months ago, we started this, and they have all adapted to it. Everybody has signed up to do this, and we're actually pretty happy with the results we're seeing. So those were a few use cases that I wanted to go over. There are many more out there in deployment. We've been really successful in implementing it. We're working on a couple of new ones that will help us speed up the network deployment process. But I wanted to thank you all for your time, and maybe if there are any questions, we'll be open to answer any questions. Anyone you want to add? Well,
I mean, just also to conclude from my side, AI is growing. It's here, but to get to a point where you have the full confidence in your AI-based models and systems, it takes time. It takes experience. Sometimes the experience is not as smooth. Sometimes it's painful, but you learn. So if one thing, I guess, I'd like to advise all the audience is, do it today. Start small. Build small proof of concepts. Start understanding the data in your networks. They're so valuable. Data is the new gold. So collect data. Do small POCs. See what use cases are out there that you can do. Start small. Grow from there. Learn. Make mistakes. That is really essential. At some point, with all those experiences, you get to a point where you have full confidence in your AI systems. So again, start. It takes time. It's okay to make mistakes. This will help you to get to a point where you have AI autonomous system. That's where we're heading eventually with autonomous agents. So your system can be automatically controlled by AI. We're not there yet. It takes time, as I mentioned, and it's a good time now to start. It's better than late. So thank you so much for your time, and really appreciate your attendance today. Thank you.